Hello class, welcome to the next lecture on signals and systems. So in this lecture we'll be moving on to frequency domain analysis of both signals and systems. Okay, so till now what we are doing, everything we were doing, we were dealing within the time domain. We were finding, seeing the different properties of signals, systems, everything, and all of those we were dealing with in the time domain. And now let's move on to the frequency domain, right? Now actually let's start from where we left off. Okay, so where did we leave in the last couple of lectures? We were dealing with the concept of convolution, right? Whether it is an convolution integral or a convolution sum, we were dealing with convolution. And what was the basic idea behind convolution? I'm not talking about the step-by-step procedure. I'm talking about that y of t is equal to x of t convolution h of t, or y of n is equal to x of n convolution h of n, right? Now let's start from this point, right? Whether it is discrete time or continuous time. Let's start from this point. Okay, let's take a system. Y of n is equal to integral summation k equal to minus infinity to infinity h of k x of n minus k. Earlier in the earlier problems, some of the problems we did, we took x of k into h of n minus k, and I am taking it the other way for a certain purpose, right? Now what I'm going to do is I'm going to put x of n is equal to e to the power j omega n, right? Now what is this? This is the complex exponential. Okay, this is a complex exponential. So what is the peculiarity of a complex exponential? We will see that. Okay, now so what will this summation become? It will be k equal to minus infinity to infinity h of k e to the power of j omega n minus k. Okay, now we are doing the summation and the variable of summation is k, so we can take this n outside, right? So it will be e to the power of j n summation k equal to minus infinity to infinity h of k e to the power of minus j omega k, that is y of n. Okay, now what are we seeing here? This is the input that we gave, right? And this is some value. Okay, this is some value. It is a finite value because no other variable n is there, and the limits are some values, maybe minus infinity to infinity. Anyway, this result won't have any particular value, any particular variable in it, right? Because the variable is n, it won't be there. There is no variable n in it. So basically what we are having is, we have y of n is equal to some constant, let's call it c for the moment, right, into e to the power j omega n. Now from your earlier mathematics classes, you should be able to identify this concept. Should be able to identify this. This is a very particular thing. You have learned this before. Okay, what is it? What is it called? It is the eigen function and eigen value. Right, you may have learned this as an eigenvector in your linear algebra class, but the concept is same. So what is an eigen function or an eigenvector? It is some function or a vector. Let's call it function here, because we are using this sort of notation. So what is an eigenfunction? It is any function, any signal, whatever, when given to a particular system, right, the output of the system will be the same. That is, if we have our eigenfunction x of t given to a system, then its output will be some constant multiplied with x of t, right? And such inputs are called as eigenfunctions, and the constant is called as the eigenvalue, right? These eigenvalue will change for each eigenfunction. Basically, we are just getting a scaled version of the input as output. That is the concept of an eigenfunction. Okay, so what did we establish here? All right, what did we establish here? We established that e to the power j omega n, that is the complex exponential, is an eigenvalue, or is an eigenfunction for what? For type of system. Which type of system? Which can use the convolution principle or the convolution property. So which type of functions can use eigenfunctions, convolution properties? The LTI system, right? So basically, at least I was trying to establish that the complex exponential is an eigenfunction for LTI systems. Right, it is an eigenfunction for LTI systems. So what? Right, so what? Earlier, in our previous time domain analysis lectures, what did we do? Particularly when we were trying to deal with convolution, we were using the concept of impulse response, right? H of t. That is when we were giving an impulse as an input, and we were getting some output as what? An impulse response. And then what did we do? Whichever signal we had as an input, we represented it as a sum of some weighted and shifted impulses, right? And we got the output as a sum of let's say weighted and shifted impulse responses, right? For discrete and continuous cases. This was what we did in the time domain analysis. We used the concept of impulse and impulse response. Now we have a similar tool which we can use in the frequency domain analysis, and that is the complex exponential. Because why are we able to do this? Because we have a class of systems which we are studying, which is LTI systems, and they have the convolution property, right? They have we can do the operation of convolution on them to get the output from certain inputs. And if for systems following convolution property, that is LTI systems, complex exponential is an eigenfunction. So what we will do is we will earlier we represented x of t and input and output in terms of the impulse function, impulse and impulse function and their relation. Similarly, what we will do is for the frequency analysis part, instead of this impulse and impulse function responses, we will be using the eigenfunction of an LTI system, which is the complex exponential. Okay. Now, before I wandered into this explanation, I stopped this here, right? I want to move a little bit further from here. So we had, right, y of n is equal to, what did we have? E to the power of j omega n into this something, right? H of k, summation h of k into something. So what I'm going to do is, I'm going to write all those things into a single thing, where h of e to the power of j omega equal to summation k equal to minus infinity to infinity h of k e to the power of j omega k. Right. What to do that this particular constant value we had, I just made it into a term, a function. This is also another function. Now what is this a function of? This is not a function of n. That is why in this scenario it will be a constant, right? This will be a constant in this scenario because this is not a function of n, but this is a function of omega. And what is omega? Omega is the discrete angular frequency. That is, as omega varies, h of e to the power of j omega also varies, right? Remember, in this context this is a constant, but in the context where we are varying omega, or in the context where we are varying the frequency, this also varies. This is a function now, and because of this property, that is because h of e to the power of j omega varies depending on omega, we are going to call this the frequency response of what? Of a discrete time system, right? Now what do we have? We have got the frequency response of a discrete time system. So till now what have we established? We have established that starting from the convolution property, for LTI systems we have an eigenfunction, and that eigenfunction is the complex exponential. Okay, and continuing from there, that eigenfunction or eigenvalue of that particular eigenfunction is something which is a constant with respect to n, but is a variable with respect to omega or the frequency, and we formally declared it as the frequency response of a discrete time system, and we wrote down a function or an expression for that. Now let's do the same thing for a continuous time system. Okay, so we have y of t is equal to integral minus infinity to infinity h of tau e to the power of j omega t minus tau d tau equal to e to the power of j omega t minus infinity to infinity. I'm just doing the same thing that we did for discrete time. I'm not doing anything new, which is equal to, now I am taking this thing into therefore we are defining, and this is the e to the power of j omega t is the eigen function for continuous time LTI systems. Okay. Now from that I am defining what this particular integral as the frequency response of continuous time system. Right. So what is the essence of what we just said? We have a system which has an impulse response, right? We give an input e to the power of j omega t or e to the power of j omega n, right? And we get an output which is h of e to the power of h of j omega into e to the power of j omega t or h of e to the power of j omega to the power of j omega n, and these terms we defined as the frequency response. Okay. Now this frequency response, it is a complex number or a complex function, right? So we can denote it as, we can find its magnitude and its phase, right? Its magnitude and its phase. Those things we will deal with detail later, but for the time being, let this be, right? Now moving on from there, what is our next logical step? Right. What is our next logical step? We have established the relationship between the eigenvalue and so many stuff. Now, the next logical step is representing any arbitrary signal as like this. What is this? Now, any arbitrary signal x of t is a weighted sum of the eigenvalue, eigenfunction of the system, right? Now, what is the advantage of this? This is similar to what we did with the impulse function. There we integrated to get the signal, but here we are just representing at the sum of eigenfunctions, right? So, what is the advantage of doing this? Now, if we extend this, we have this. This is very significant. Why? Because we just converted our convolution into a multiplication. We just converted our convolution into a multiplication, because convolution is a, let's say it is a sort of difficult operation to do, and once we get this in this form, and you will see it later when we deal with the different transforms, this allows us to convert our convolution operation into a multiplication in the frequency domain, which makes our life much easier. Okay, so the essence of frequency domain analysis is representing our signal in terms of e to the power of j omega t, the complex exponential, right? Now we can do this in multiple ways, because representing signals, we basically have what? We basically have four classes of signals, right? We have periodic signals and we have non-periodic signals, right? We have continuous time signals and we have discrete time signals, and we need to find different tools for representing each of these using what? Using the same complex exponential only. Complex exponential. This complex exponential is the centerpiece of our logic here. It is probably one of the most important concepts for our signal processing or representation of signals, whatever we write. So what do we do? And the continuous version of these you have already learned. What is this? Which is Fourier series and Fourier transform. Right. Fourier, when he invented this, he was not trying to represent signals as complex exponential. His motivations were different. It had to do with differential equations and heat equations and such. But the thing is that this Fourier analysis, frequency analysis, which is such a strong tool, it is such a powerful mathematical tool that we are using it in multiple domains, and our system or signal domain, signal or system analysis domain just happens to be one of those. Right, it is a very vast thing, and what we'll do in our upcoming lectures is we'll boil down this Fourier analysis into whatever we want, right? And we have discrete time. Let's call this Fourier series, Fourier transform. We have discrete time Fourier series for discrete time periodic signals. And we have discrete time Fourier transform for discrete time non-periodic signals, right? And for most of these the signals, the mathematical expressions will look very much similar, just that there will be an integral in the case of continuous time, there will be summations in the case of discrete time. They look very similar, very much similar, but there are some key differences. They have different properties. Even periodicity is an issue, not an issue. There, periodicity of the transforms or the series is a property. Things are like that. Okay. Now there are two more transforms, Laplace transform and Z transform, that you will be learning in the frequency domain analysis. What is that? What is this? What are these four? These four are used for representing signals, right? And if so, these are used for system representation and analysis. By that doesn't mean that we cannot use Laplace transform for representing or analyzing a signal. It can be, because Fourier transform is a subset of Laplace transform, right? Fourier transform is a subset of or a special condition of Laplace transform, and this we are using for continuous time systems, and this Z transform we are using for discrete time system, right? So this is the bird's eye view of what we are going to see in the upcoming lectures, right? Now before I wind up this lecture, a word about transforms. So what are transforms? You maybe you in your math classes you may have done problems regarding this. You may have solved so many questions, right? You may have So what are transforms? Basically, and you may have an idea regarding this because we have dealt with Laplace transform in our previous course, which was network theory. Right there, what did we mostly use it for? We sort of use it for solving differential equations, right? See, that is the thing. These things, like these transforms, series, and such, they are mathematical tools, and they may have been originated for some other purposes, but now we are using it for our purpose. Anyway, what are transforms? Transforms, suppose we have, and whatever I am talking now, I am talking in terms of our signal and system context. Okay, we have, suppose we have a signal in our time domain, right? We can see certain properties of this in this one. We can analyze it in a certain way. We can even process it in a certain way. But what we in transformation, what we are doing it here, the independent variable is t, right? Here the independent variable may be something else. In the case of S domain Laplace transform, we call this the S plane, where the variables are sigma and j omega, right? What we are doing is we are taking the same entity and we are representing it using different variables. And when we are representing the same entity using different variables, what happens? The expression changes. And what is the other thing? New properties emerge, which we were otherwise not able to analyze in the other set of variables which we were using. That is, we are transforming this thing, this quantity, whatever we have, into another thing. We are transforming it, right? And this is a very powerful tool. In the case of series, we are not transforming it. Yes, you can say we are transforming it in a sense, but basically what we are doing, we are representing it as a, we have a quantity and we are representing it as a what? Sum of certain terms, right? We are representing it as a sum of certain terms, and these certain terms in our particular case are what? The complex exponential, weighted in according to the different situation, right? So in the case of series, we are not essentially transforming it, but yes, this series that we are writing, it can be represented differently. We will come to that in detail when you we'll get there. You will get a better understanding. Now I'm just trying to give you a bird's eye view, right? So I'm going to leave you there, and I just wanted to give you a brief idea or a bird's eye view of this, and if possible, please do some digging up regarding the complex exponential, what this is, right? Because this is a very crucial to our endeavor. Okay, so that I'm writing on my lecture. See you in the next class. Thank you.